Welcome to this week's third and the last lecture. In the previous lecture, we have learned how to find this P matrix that would bring the matrix A into its Jordan canonical form. In this lecture, we are going to finalize that topic. In the lecture notes, I have an example, but as I told you in the last lecture, I won't solve that example because it's already in the notes, and I think I have explained this concept sufficiently enough. So the example is as follows. So we have an A matrix in C 4 by 4 and single eigenvalue, and we are given that Mi is equal to 2. Okay? So single eigenvalue name is lambda I. So in that case, we know that d of s is equal to s minus lambda I to the power 4, because that's the size of the matrix and we have a single eigenvalue. And m of s is s minus lambda I to the power 2. And the task is find all possible Jordan canonical forms and P matrices, corresponding P matrices. Okay? So in this case, we have solved the first part of this question. So you need to find all possible Jordan canonical forms, and it was just like this. So A is equal to, so I have sigma I is equal to A minus lambda I identity, and we know that we have then null space of sigma I and null space of sigma I square, and this is my largest null space. And the dimension of this thing should be 4 because of the characteristic polynomial power. And in this case, the only thing that we don't know is the dimension of the null space. How many linearly independent eigenvectors that we can have. So this dimension can be 3, 2, 1. And for each of the cases, there might be a different Jordan canonical form for the corresponding A matrix. Okay? And for each A matrix, and for each of these dimensions, for each of the Jordan canonical forms, you will be able to find a different P matrix. All right? So the example solution is already inside the notes. You can check it if you would like to learn more about this example. And remember that this dimension 1 was not possible. In that case, you cannot find the Jordan canonical form because there is no such A matrix that would have dimensions 1 and 4. Okay? And in that case, finding the P matrix is also impossible since Jordan canonical, since there is no such A matrix. Instead, in this lecture, I'm going to solve the numerical example in the notes, and that is also going to contain some ideas from the same topic. So I want to start with a clean black whiteboard. So we have the following example. A matrix is given to us as follows: 1, 0, 0, minus 1, 1, 1, 0, 1, 0, 0, 1, 0, and 0, 0, 0, 2. Okay? The characteristic polynomial is given to us, s minus 1 cube and s minus 2. And the tasks to achieve are: what is M of s, what is the Jordan canonical form, and what is the P matrix that would put the matrix into this Jordan canonical form. Okay? So we are looking for a P matrix that would satisfy this equation. So now we are given the characteristic polynomial, but that is because really I do not want to find the characteristic polynomial myself in the lecture, so not to spend time on that, which is a straightforward procedure. So please yourself, as an exercise, try to derive the characteristic polynomial of this A matrix and see that it is going to be something like this. All right? Expand this d of s and see that the characteristic polynomial is the same. So now let us try to look at the minimal polynomial. So the minimal polynomial, we know that if we have a characteristic polynomial like this, the minimal polynomial is going to have the following structure. So I will have S minus 1 M1 and S minus 2 M2. Okay, and I know that M1 and M2 can have different ranges. So M1 is going to be between 1 and 3, and M2 is going to be between 1 and 1. That means that M2 has to be equal to 1. Okay, so I really do not have to use any M2, unknown M2 here. It is exactly equal to 1. So the only question mark here would be, what is M1? Okay, and we know that we can identify this M1 from the null space dimensions. The first thing that I'm going to do is to calculate these matrices. Let us define sigma 1. It is A minus lambda 1 identity, and lambda 1 is 1 here. So it's going to be A minus identity. And sigma 2 is A minus lambda 2 identity, and lambda 2 is 2. That means this is going to be A minus 2 identity. So let me write the matrix sigma 1 here. Sigma 1 is going to be A minus identity. So from the diagonals I will subtract 1. So I would have 0, 0, 0, 1 here, and the rest of the matrix is exactly the same. So I have this matrix, and I would like to find the dimension of the null space of this matrix. Dimension of the null space of sigma 1 is going to be the rank of this matrix. I see that I have only two linearly independent columns, or this one and this one, and the other ones are linearly dependent with the first two. That means that the dimension of the range space of this matrix, or the rank of this matrix, is 2, meaning that by the rank nullity theorem, dimension of the null space should be 2. So with 2, did we reach the largest possible dimension, which is 3, which is 3, the characteristic polynomial power? No, we did. At the power 1, we didn't reach the largest possible dimension. We didn't reach the characteristic polynomial power. That means that I need to increase the power of the matrix here. So I know that in that case it has to be the null space dimension of sigma 1 square should be exactly equal to 3 actually. So it cannot be larger than 3, because that is the maximum dimension. So as soon as I see this 2 here, that the minimal polynomial is going to have S minus 1 square and S minus 2. Okay? So let me take the square of this matrix. So I would have here and zeros, and I would have 0, 0, 0, 1. So you see that in this case I have only two non-zero columns. That means that the rank of this matrix is 2. No, of course not. Those two columns are linearly dependent with each other. Therefore, I have only here one linearly independent column, meaning that the rank of the matrix is just equal to 1. So that means that the dimension of null space of sigma 1 square is equal to 3 in this case. So we see that we have reached the largest possible dimension at the power 2. That means that M1 is going to be 2. Okay, so I can write here this 2, and I can erase this. So we have identified the characteristic minimal polynomial in this case. And now I'm going to go into the matrix sigma 2. Let me look at the dimension of that one as well. Sigma 2 is A minus 2 identity. I will subtract 2 from the main diagonal here. So I have minus 1, minus 1, minus 1, 0. And the rest of the matrix should be the same. So I would have 0, 0, 0 here. And finally, minus 1, 1, 0. So this is sigma 2, and I would like to learn about the dimension of the null space of this. How many linearly independent columns does this matrix have? So we see here that this column is linearly independent with this column, and this third column is also linearly independent with the first two. So I see that there are 3 linearly independent columns, meaning that the rank is 3, so null space dimension is 1. Dimension of null space of sigma 2 is 1. So you see that we have reached the largest possible dimension, which is the characteristic polynomial power of the same eigenvalue. That means that in the minimal polynomial I will have 1 power here, the power 1, multiplicity 1 in the minimal polynomial, because we reached the largest possible dimension at the power 1 here. So that confirms that our minimal polynomial is already found here. So now I'm going to look at the Jordan canonical form of this matrix. So let me try to look at these null space dimension. Null space of sigma 1 and null space of sigma 1 square. The dimension of this one is 2 and dimension of this one is 3. And that is the largest possible dimension. Okay? In this case, in order to be able to find the corresponding parts of the Jordan form, you would work with the corresponding sigma 1 matrices or sigma 2 matrices for each eigenvalue. Okay? So you need to consider eigenvalues one by one. And for the eigenvalue, first eigenvalue, I would have these null spaces. And how many Jordan blocks are there? So I know that this is the number of Jordan blocks. So there are 2 Jordan blocks. And what about their sizes? I see that the number of Jordan blocks whose size is larger than or equal to 2 is going to be this difference. So I would have, in this case, that number equal to 1, meaning that there is 1 Jordan block whose size is larger than or equal to 2. Do we have any Jordan block whose size is larger than or equal to 3? In this case, no, because the minimal polynomial power is 2. That means that the size of the largest Jordan block would be 2 in this case. So that means that I have 1 Jordan block with size 2, and I have 1 Jordan block with size 1. Okay? So here, if I try to give you the Jordan canonical form in this case, for the first eigenvalue 1, I would have 2 Jordan blocks whose sizes are 2 and 1. So I would have the corresponding part of the Jordan canonical form would be in this form. I have a 2 by 2 block and 1 by 1 block. Okay? And what about the other eigenvalue? So null space of sigma 2 is the largest possible null space in this case, and its dimension is 1. How many Jordan blocks are there? There is only 1 Jordan block. And what is the size of the number of the Jordan blocks whose size is larger than or equal to 2? So the next null space has equal dimension because it's equal to this largest null space. So there are no blocks of size 2 or larger. Okay? That means that there is only 1 Jordan block with size 1 here. So, and that is for the second eigenvalue, which means that this is going to be my Jordan canonical form here. This is the other block corresponding to the other eigenvalue. And the rest is equal to 0. Okay? So I have found the Jordan canonical form. And now we are going to go into the task of finding the P matrix, finding a P matrix that would put this matrix into its Jordan canonical form. So I'm going to start with these concentric null spaces, and this is my null space of sigma 1 and null space of sigma 1 square. Dimension of this one is 2, and dimension of this one is 3. Let me try to find my chains here. Here, for the first eigenvalue, I have 2 Jordan blocks whose sizes are 2 and 1. That means that I will need to find 2 chains whose sizes would be 2 and 1. Corresponding to the Jordan blocks. Okay, so I will start from the outermost disk here. I will choose an x. X is going to be inside null space of sigma 1 square, and x will not be inside null space of sigma 1. Okay? I am looking for a generalized eigenvector here. That vector should not be inside the eigenspace, so it is not going to be an eigenvector, but it's going to be inside this larger null space. So what does that mean? That means that sigma 1 square x is equal to 0, but sigma 1 x is not going to be equal to 0. Must not be equal to 0. Okay? So I'm looking for a non-zero vector in the null space of this sigma 1 square, but not in the null space of this matrix here. So when I multiply x with this matrix, I need to get 0, but when I multiply x with this matrix, I need to get a non-zero vector. So if you look at the vectors inside the null space of this matrix, you can see that I can choose 0, 1, 0, 0 in the null space, because that means that I will take the second column as the result of the multiplication, which means that that vector is inside the null space. So I can choose x equals to 0, 1, 0, 0. So here this choice really is not unique here. I can find one more vector here that would be inside the null space of this one, but that is not inside the null space of this one. So for example, can you choose x as follows: 0, 0, 1, 0? Can you choose x as this one? So you see that that x, when I multiply it with this matrix, is going to give me 0 as the result, and therefore that second vector x there, 0, 0, 1, 0, is inside the null space of this one. But what about this one? It is, if I multiply x with sigma 1, so you see that it is again going to be giving me the 0 result. That means that that second x vector is in the null space of both of these matrices. So really it doesn't satisfy the required conditions. So x really cannot be equal to this one, because it doesn't satisfy the second condition then. This x is also inside the null space of sigma 1. It is an eigenvector at the same time. But there can be another x I can choose here. So, and that x can be 1, 1, 1, 0, 1. Okay? So if you look at this x, then if you multiply this matrix with it, you would again get 0. So it is the null space of, it's in the null space of this matrix. But if you multiply this matrix with that x, you will see that it is not in the null space of this matrix. Okay, so here the x selection is not really unique. Okay, so there are infinitely many P matrices that would bring this matrix into its Jordan canonical form. So P really is not unique here. But here, so this is also possible. And this is of course possible, but I'm only going to select this one and will continue with that one. So I won't think about this second one. So in order to not cause confusion, I will erase this. So this is my x, and then I will calculate its continuation. It's going to be sigma 1x here, and that vector should be an eigenvector. So sigma 1x is sigma 1 times this vector is going to be, I would have this matrix times that x vector, and it's going to give me 1, 0, 0, 1. And I know that this vector is in the eigenspace, it is non-zero. That means that it should be an eigenvector. I can check it, multiply 1, 0, 0, 1 with the A matrix. In that case, you would sum the first and the last columns here, and that is going to give you 1, 0, 0, 1. Okay? That means that A times that vector is equal to that vector. That means that this vector is an eigenvector of the A matrix corresponding to the eigenvalue 1. All right? So this is going to be my first chain, sigma 1, x, and x. Okay? And this is the chain corresponding to this 2 by 2 Jordan block. Now I'm going to try to complete this chain into a full basis for this outer null space, the largest null space. I see that in the chain I have 2 linearly independent vectors, but this null space has dimension 3. That means that this single chain will not be able to constitute a basis for this largest null space. That means I need more chains in order to be able to find a basis vector for this largest null space. So here I will first look for another vector y in this outer disk here. So do you think I need to find a vector in this outer disk? So you see that the dimension increase from this inner circle to the outer circle is 1. So the dimension increases from 2 to 3. That means that I shouldn't look for my additional chain here in the outermost disk, because from 2 to 3 and this x takes the space of one dimension already. Okay, so there is no space for us to find a y vector here. Okay, and if I find the y vector, the continuation of that vector here inside the null space is going to be linearly dependent with this sigma 1x. So that y vector would be useless for us. Okay, so there is no space for starting the second chain from here. That is why I'm going to move one space inside, and I will look here the dimension. The dimension here is 2, and I have already found a single vector here. That means that there is space for one more vector here, and I will call that vector y. So this y is going to be inside null space of sigma 1, and y is not going to be inside sigma 1 to the power 0. This is sigma 1 to the power 1, and this is sigma 1 to the power 0. But what is this? This is null space of the identity matrix, and null space of the identity matrix is always composed of only the 0 vector. That means that instead of writing this condition like this, I can just write y is not equal to 0. Okay? If y is not in this smallest subspace, which is composed of only the 0 vector, then y should not be the 0 vector. Okay? So these are the conditions for starting the second chain here, and I need to and I have also another condition on top of this. So I will form my second chain y from a single vector here inside the eigenspace, and I need to have an additional condition to make this chain linearly independent with this first chain. Okay? And we know that that condition should be that the innermost vectors in the innermost circle, vectors in the eigenspace should be linearly independent. So here I am looking for a y inside the null space of sigma 1, and furthermore y should be linearly independent with sigma 1x. So the y that I find should be linearly independent with this vector. Okay? So I'm looking for a y vector in the null space of this matrix, and that vector should be linearly independent with this vector. Okay? So I see already here that another vector in the null space of this matrix would be 0, 0, 1, 0, because the third column is 0. So 0, 0, 1, 0 would be in the null space, and furthermore 0, 0, 1, 0 would be linearly independent with this vector. Okay? So I can choose here y is equal to 0, 0, 1, 0. Okay? This is the y that satisfies both of these conditions. Here, this selection is not really unique either. Instead of this y, I can select, for example, y equals to 1, 0, 1, 1. This is also possible in this case. So because this is also an eigenvector of this matrix. Okay, and it is linearly independent with this one. Okay, it is linearly independent with this one. All right. So here, but in order to not confuse you, I'm going to erase this alternative here, and I will think that I have selected this y. But know that these selections really are not unique. So I have now my total number of vectors is 2 plus 1 is 3, and I have reached the dimension of this largest null space. That means that for the first eigenvalue I can stop here. Okay? And that means that I am going to go into the second eigenvalue. The second eigenvalue has only a single concentric null space. Okay? It is going to be here, null space of sigma 2, and its dimension is just 1. So in order to be able to find the vector or the chain corresponding to that, I will start with the z vector here, and it is the same as these conditions. Z is going to be inside null space of sigma 2, and z should be non-zero. Okay. And here I need to find a single non-zero vector corresponding to this, corresponding to the null space of this matrix. So we see that in the null space of this matrix, I have the vector 0, 0, 0, 1. Okay? So I can choose my z vector as 0, 0, 0, 1. So how many eigenvectors does this matrix have? How many linearly independent eigenvectors can this matrix have? So for the first eigenvalue, there are two eigenvectors. So this sigma 1 x and y are eigenvectors. And furthermore, z is an eigenvector for the second eigenvalue. So in total, this matrix has 3 linearly independent eigenvectors. Since the matrix doesn't have as many linearly independent eigenvectors as its size, it's not diagonalizable. So this matrix is not diagonalizable, and we see it from the Jordan canonical form already. Jordan canonical form is not diagonal. If the minimal polynomial was s minus 1 times s minus 2, then it would have been diagonalizable, and in that case the Jordan canonical form would be a diagonal matrix. So now I have already found all of my vectors. Now I can fill in my P matrix. So I will fill in this P matrix out of the vectors I have found. So I will first put the chain with 2 elements. So sigma 1 x and x. And then I will put the chain with 1 element for the second eigenvalue. Then I will put y. And finally I will put the chain for the second eigenvalue, which is going to be z. Okay? And I know that 3 columns of this matrix are eigenvalues. Sigma 1, x, y, and z are eigenvectors. And x is not an eigenvector. X is a generalized eigenvector. And you see it by multiply that x with this matrix, and you will see that you won't be able to get a scalar multiple of that x vector. That means that this x is not an eigenvector, but it is a generalized eigenvector. So here, this P then is going to be the following: 1, 0, 0, 1, and 0, 1, 0, 0, and 0, 0, 1, 0, and finally 0, 0, 0, 1. Okay? So this is the P matrix that brings this matrix into its Jordan canonical form. So this really completes this example, and actually this really completes the most difficult part of this course. So far, this Jordan canonical form, finding the P matrix, they are probably the most difficult parts of this course. And from this point on, we're going to see the remaining topics. As I told you, there are 2 topics: Hermitian matrices and the functions of a matrix. And once you know the theory that we have seen so far, if you know them well, then you're going to see that it is very easy. The topics of Hermitian matrices and Jordan canonical forms will be very easy once you know this theory. Okay? So now we are at an important point of this course, and we can start with the Hermitian matrices. So okay, let us start with Hermitian matrices. So I will start by first defining what an Hermitian matrix is. An n by n complex matrix, in general complex matrix A, is called Hermitian if and only if A complex conjugate transpose, okay, is equal to A itself. Okay? So I have this property. In other words, this means that complex conjugate transpose of A is equal to itself. This is in other words. Okay? So we know that I showed the complex conjugate transpose with the letter H here. Sometimes, as the Professor Emre Özkan, they show it with the letter star, with the star character, but I'm going to show this as a Hermitian. Okay, this is complex conjugate transpose. So if a matrix is Hermitian, then its Hermitian is equal to itself. All right. So I have this property. So if the matrix A is real, if the matrix A is real valued, which means that all of its elements are real quantities, in that case we have then A Hermitian is equal to A transpose. Okay? So if the matrix A is real, then A Hermitian, so complex conjugate transpose is going to be only transpose, because complex conjugate of a real quantity would be equal to itself. Okay? So in that case, an Hermitian matrix means that A transpose is equal to A. Okay? But this is the condition for a symmetric matrix. So we see that if an Hermitian matrix has all of its elements real quantities, then that matrix is going to be symmetric. So Hermitian matrix is therefore a generalization of the symmetric matrices. Symmetric matrices are a special case of the Hermitian matrices. So remember my famous example that I used in the previous lectures. So this A had the eigenvalues lambda 1 and lambda 2, which were 3 and 1. Okay? And we know that the eigenvectors for these eigenvalues were 1, 1, and E2 was 1 minus 1. Okay? In this case, we see that this Hermitian matrix had real eigenvalues. So it didn't have any complex eigenvalues. And furthermore, we had eigenvectors, and these eigenvectors were orthogonal to each other. Okay? So the inner product of E1 and E2 would be 0 here. So we are going to see that these results here for this simple matrix, they were not a coincidence. Okay? We will see that all Hermitian matrices would satisfy this type of properties. All Hermitian matrices would have real eigenvalues, and furthermore, their eigenvectors corresponding to distinct eigenvalues would be orthogonal to each other. Okay? So that is a general property of the Hermitian matrices. These properties are not specific to this simple matrix, but they can be generalized to any matrix, any Hermitian matrix. So now, before we go into the properties, I will remind you this inner product properties. So suppose that I have an inner product xy. This inner product is y Hermitian x, L2 inner product. Okay? So there were some properties of the inner products, and you have seen some of those properties as the axioms of the inner product. We know that yx inner product is equal to x and y inner product complex conjugate. So I have conjugate commutativity of the inner product operation here. Okay, if I change the elements of an inner product given like this, then I would have complex conjugate property. Okay, so y inner product of y with x is the complex conjugate of inner product of x and y. This was one of the axioms of the inner product. And another property that you have seen, if you have a constant in one of the arguments of the inner product, then if it is in the first argument, then you can take it outside directly. Okay? And you have probably seen that if the alpha is in the second argument, then you can take that alpha outside by taking its complex conjugate. Okay? So this is called homogeneity with respect to the first argument of the inner product, and this is called conjugate homogeneity or conjugate scalability. Okay? For the inner product. So you have seen already these properties. And remember, I have also introduced one such property in one of the lectures. I don't know which, I don't remember which, but if you have an inner product of this form, then I know that this inner product is going to be the complex conjugate or Hermitian of the second argument. So it is AY Hermitian times X. Okay? According to the definition, I have this one. And this is equal to Y Hermitian, A Hermitian, X here. And you see that here, I can write this inner product in an equivalent way as follows. Y Hermitian times A Hermitian X. Okay? But this is the inner product of Y with A Hermitian X. Okay? So you see that when you have a matrix multiplication in one of the arguments of the inner product, you can take that A multiplication to the other argument by taking its Hermitian. Okay? So you can take this A to the other, in front of the other element, in front of the other argument, by writing here A Hermitian. So this is the important property that we are going to use in proving the properties of Hermitian matrices. So A X A Y is A Hermitian X Y according to this inner product. So these three properties are the properties satisfied by all inner products. Okay? So because these are coming from the inner product axioms. On the other hand, this last property here, this last property that I have written is only a property of this specific L2 inner product. It is not a property of other inner products that you can define. All right? So this is not an axiom of an inner product, actually. It is only specific to this L2 inner product. So these are the properties of the inner products that you need to remember. So now I will start with the properties of the Hermitian matrices. So we will start with the theorem. Let A be Hermitian. In this case, then XAX, the inner product XAX, is real, let us write, is real for all X in Cn. Okay. This is the first property of the Hermitian matrices. If the matrix A is Hermitian, such an inner product, we are going to be using this L2 inner product here, this inner product, X with AX, inner product of X with its transformation, would be always real. So this inner product in general is a complex quantity. And here we are told that if A is Hermitian, such an inner product would always turn out to be real for all X's. All right? Let us try to prove this. So in the proof, I will show that the complex conjugate of this inner product is equal to itself. Okay? So I will take the complex conjugate of this inner product. This bar, over bar, shows the complex conjugate operation. Then this is going to be, by the properties of the inner product, this is going to be the arguments exchanged, okay? Swapping arguments here. This is equal to AXX. And here is is what I'm going to do. I'm going to take as A to the other argument by taking its Hermitian. So this is equal to XA Hermitian X. Okay? But you see that A Hermitian is equal to A because the matrix A is Hermitian in this case. That means that this is going to be equal to XAX inner product. Okay? But that shows us that XAX complex conjugate is equal to XAX. Okay? But this shows that this quantity should be real, because if it is complex, if its imaginary part is non-zero, then it wouldn't satisfy such a property. Its complex conjugate would not be equal to itself if it was complex. Okay? As a result, we can say that XAX is real. Okay? So let us look at what XAX is. I'm going to use the definition of this L2 inner product here. And in this case, this XAX is nothing but AX Hermitian times X itself, okay, according to this definition of the inner product. And that is X Hermitian, A Hermitian X, okay? But A Hermitian is equal to A. As a result, I have X Hermitian AX. So this is called a quadratic form in mathematics. So if a matrix A is Hermitian, then this quadratic form is always a real quantity. Okay? This is a quadratic form. And if the matrix A is Hermitian, then this quantity is real. So now we can go into other properties of the Hermitian matrix. Now we can start with the eigenvalues theorem. Let A be Hermitian. Then the eigenvalues lambda I of A are real. So we are said here that the eigenvalues of A are actually real. Okay? So in this simple example is not really coincidence. These real eigenvalues are not really forming a coincidence. Instead, they are the general property. They're coming from the general property of Hermitian matrices. This matrix is symmetric, so it's Hermitian. Okay? So we see here that because this matrix is real valued, then it's Hermitian. That means that its eigenvalues should be real. So now let us try to prove this. So let lambda I be an eigenvalue of A with the corresponding eigenvector. Eigenvector EI. Okay? So lambda I is an arbitrary eigenvalue of the matrix A. That means that it needs to have at least one eigenvector, and that means that this AEI is going to be satisfy this equation when EI is not equal to the zero vector. Okay? This eigenvector should satisfy the eigenvector property. Okay? So now I'm going to write some quantities here. So here we see that XAX, this is the real property of such an inner product is correct for all x's in Cn. Okay? So when I choose x as an eigenvector, this property should also hold. Okay? So that means that if I, instead of x, if I substitute EI, then this should be real. Is always real. Okay? So here is what I'm going to do. I will take this A to the other side. EI. So if I take this A to the other side, I will write A Hermitian EI. EI is real. Okay? And then I'm going to use the Hermitian property. If A is Hermitian, then A Hermitian is equal to A itself. So I have EI is real. Okay? But AEI is lambda I EI. So lambda I EI, EI is real. Okay? And now I can take lambda I outside. This is in the first argument of the inner product. I can take it outside. So lambda I EI is real. Okay? And in the properties of the inner product, you have seen that such an inner product of a vector with itself is always real, and it should always be positive or zero. Okay? And it is going to be non-zero if the vector is non-zero. In this case, I know that EI is non-zero, so that means that this quantity, EI inner product, is always going to be real and positive. Okay? But you already know that also from the following property. This EI inner product is nothing but the norm square of EI times lambda I. Okay? This is always real. I know that this is real and positive. Why is it positive? Because it can be either 0 or positive, and when the vector inside is non-zero, this should be positive. And the vector, eigenvector, is by definition is a non-zero vector. Okay? So that means that this is larger than 0. So that means that this quantity should be just real. Okay? So this EI square is real and positive, and the overall multiplication is real. If the overall multiplication is real, then this lambda I should be a real quantity. Because if lambda I is a complex number, then when I multiply it with a positive real number, the result should be complex. Okay? That means that here lambda I should be real. Okay. In the notes there is another but a little bit longer proof. You can look at that proof as well. So really, when we have a result, it can have multiple proofs at the same time. And here I wanted to do the proof in this way, but there is an alternative proof in the lecture notes. You can check the argumentation in that proof as well. So now we know that the eigenvalues, or any eigenvalue of a Hermitian matrix, is actually a real quantity. There cannot be complex eigenvalues of Hermitian matrices. Okay? So now let us go into the eigenvectors. In the earlier example, the simple example, we saw that the eigenvectors are orthogonal to each other. So they were eigenvectors belonging to distinct eigenvalues. The eigenvalues were 3 and 1. They were distinct eigenvalues, and the eigenvectors belonging to them were orthogonal to each other. So we see now in the next theorem that this is a general property of Hermitian matrices. Let us write theorem. Let A be Hermitian. Let lambda I, lambda j be two distinct eigenvalues. With eigenvectors EI and EJ. Okay? So in this case, because these eigenvalues are distinct, I know that lambda I is not equal to lambda j. then the eigenvectors EI and EJ are orthogonal. Orthogonal with respect to which inner product? It is L2 inner product. EI, EJ, L2 inner product. They are orthogonal to each other. Okay? So let us prove this eigenvector property. I will start with this inner product. So I have EI, AEJ. Okay? So this is equal to A times EJ is lambda J times EJ. EI, lambda J times EJ. Okay? And I can take this scalar multiplication here outside the inner product. This is in the second argument. As a result, I can take lambda J by taking its complex conjugate. Lambda J complex conjugate EI, EJ, inner product. But we have already seen that the eigenvalues of a Hermitian matrix should be real. That means that this lambda J complex conjugate is equal to lambda J itself. Lambda J, EI, EJ. Okay? So this is my first equality. EI, AEJ is equal to lambda J times EI, EJ. Okay? So now here I will try to show another equality which is equal to this quantity here, and then I will try to go into the main result. So let us start with EI, AEJ, and let us use the inner product property with A here. If I want to take this A to the other argument, then I need to take its Hermitian. So this is AEI times EJ. Okay? I have a Hermitian here. Okay? A, when I take it to the other argument, I need to take its Hermitian. But a Hermitian is equal to A itself. Alright? So I have here A, EI, times EJ. Okay? Now AEI is nothing but lambda I, EI, EJ here, and I can take lambda I directly outside. Lambda I, EI, EJ. So now you see that I have started with the same quantity here, but I have shown that it's equal to a different quantity. In this case, I had lambda J, EI, EJ, and in that case, the same quantity has to be equal to lambda I times EI, EJ. Okay? So that means that this EI, AEJ is also equal to lambda I, EI, EJ. Okay? Inner product. So this is my second equality. So I see that the same quantity is equal to these two different quantities. Okay? So that means that lambda I, EI, EJ should be equal to lambda J, EI, EJ. Because they are equal to the same quantity. Okay? And now let me take the right hand side to the left. So I will take lambda I minus lambda J. So this is a scalar times EI, EJ has to be equal to the scalar 0. Okay? Now this is a multiplication of two scalars and the result is equal to 0. That means that either this number is equal to 0 or this number is equal to 0, or both. Both are equal to 0. Okay? Can this number be equal to 0? I know that in this case the eigenvalues are distinct. So we know that lambda I is not equal to lambda J. That means that this number is a non-zero number. Okay? That means that this inner product should be equal to 0. Okay, so I started with two distinct, arbitrary but distinct eigenvalues, and I have shown that their corresponding eigenvectors should be just orthogonal. And this is for the case of the Hermitian matrices. What is different to the case of general matrices? In general, when the matrices are not Hermitian, their eigenvectors belonging to distinct eigenvalues would always be linearly independent. Okay? So we have seen actually for the distinct eigenvalued matrices. This case was shown in the case of distinct eigenvalued matrices. For distinct matrices with distinct eigenvalues, we have seen that eigenvectors were linearly independent. Eigenvectors belonging to distinct eigenvalues were always linearly independent. So this is true in general. Even when the eigenvalues are repeated, if you have two eigenvectors belonging to distinct eigenvalues, then those eigenvectors should be linearly independent. Okay? For general matrices, eigenvectors belonging to distinct eigenvalues are actually linearly independent. And for Hermitian matrices, they are not only linearly independent, but they are at the same time orthogonal to each other, which is a much stronger condition. Okay? So that is the difference between the general case and the Hermitian case. So let me write this as a fact. So the general case eigenvectors belonging to distinct eigenvalues are linearly independent. Hermitian case eigenvectors belonging to distinct eigenvalues are orthogonal. Okay? So this is the perfect property of Hermitian matrices. So now we have seen the result on eigenvectors. Now we can look at the minimal polynomial of an Hermitian matrix. Let us write a theorem. Let A be Hermitian. Then its minimal polynomial has the form m of s equals to s minus lambda 1, s minus lambda 2, going until s minus lambda k. Okay? Where lambda 1 to lambda k are the distinct eigenvalues of A. So in this case, we are claiming a very, very specific thing about the minimal polynomial. In general, for general matrices, we know that the minimal polynomial powers can be between 1 and Ri. Okay? But in this case, this theorem is actually claiming that in this case, the minimal polynomial powers should all be equal to 1. Okay? So the theorem is claiming that, in other words, if A is Hermitian, then Mi is equal to 1 for all I. all minimal polynomial multiplicities, all minimal polynomial powers of the eigenvalues would be 1. Okay? This is a very, very important property. And we are going to see that this means something very, very important about a Hermitian matrix, or about the Jordan canonical form of an Hermitian matrix. Here, because all of these powers in the minimal polynomial are 1, we know that the size of the largest Jordan block for each eigenvalue would be 1. Minimal polynomial powers are always equal to the size of the largest Jordan block for each eigenvalue. That means that in this case, the size of the Jordan blocks for each eigenvalue are 1, but if the Jordan canonical form are formed out of 1 by 1 Jordan blocks, the Jordan canonical form would be diagonal. Okay? So this theorem actually implies that the Jordan canonical form of an Hermitian matrix would be diagonal, meaning that any Hermitian matrix is actually diagonalizable. Okay? So, in other words, Jordan canonical form of A is diagonal. Now, that's not right in other words, but this implies that Jordan canonical form of A is diagonal. Then I can also say that A is diagonalizable. So a Hermitian matrix is always diagonalizable. In the area of signal processing, people are always working with covariance matrices, which are always Hermitian matrices. In the telecommunication as well, people in the areas of telecommunication or statistical signal processing, they are always working with covariance matrices, which are always Hermitian matrices. Okay? And as a result, the Jordan canonical form of such matrices, such covariance matrices, would always be diagonal. Therefore, in general, people from statistical signal processing or telecommunication, they would not know about the general Jordan canonical form topic. So, because they are always using a very specific matrices which are always diagonalizable, therefore they only know about this diagonalization concept, but not about the general form of diagonalization, which is the Jordan canonical form. So let us try to prove this. Okay? What are we going to prove? We are going to prove that MIs are always equal to 1 for a Hermitian matrix. Okay? So what do we have to show here? Proof. And we are going to try to prove this fact from the null space dimensions. Okay? We know that if I define null space of A minus lambda I identity, if the minimal polynomial power Mi is equal to 1, then this becomes the largest null space. Okay? That means that if I increase the power of the matrix here to 2, this null space would be the same as the largest null space. Okay? So the minimal polynomial powers are equal to 1 if the largest null space is reached at the power 1. Okay? If the eigenspace is the largest null space, then minimal polynomial powers would be 1. Okay? That means that when Mi is equal to 1, this largest null space will not be growing when I increase the power here to 2. So this is what I need to prove here. So we will prove that there is such a null space equality, which means that the growth of the null spaces stop at the first power. So this is the largest null space. So equality is satisfied when we increase the power. Okay? So here, that means that we're going to have to prove this equality to show that MIs are equal to 1. Because if this equality is satisfied, then this means that this is my largest null space, and that means that mi, which is going to be the power of this matrix in this null space, is going to be equal to 1. Okay? So we need to prove this. But what is this? This is sigma I is equal to null space of sigma I square. All right? Sigma I is A minus lambda I identity. All right? So now here, this is a set equality, and I need to prove this set equality. Proving set equalities is always done in the same manner. I first show that this null space is a subset of this null space, and then I show that this null space is a subset of this null space. Okay? If I show that both of these relationships are correct, then the only possibility is the equality of these two null spaces. So in the earlier parts of this course, we have already proved that such a subset relationship would always hold. Okay? In the earlier parts of this course, when we looked at the structure of these null spaces, we have already shown that these null spaces would either grow or remain equal. Okay? So this was already shown. This was already shown. So the only thing that I need to show is this one. Okay? What is this? This is null space of A minus lambda I square is a subset of null space of A minus lambda I identity. Okay? I need to show this subset relationship. So it means that I need to show the following picture. Null space of A minus lambda I identity is like this, and null space of A minus lambda I identity square is a smaller or equal set. Okay? So I'm going to take an arbitrary element from this null space. Let X be an element of null space of A minus lambda I identity square. Okay? And after taking an arbitrary element from here, I will show that it is also an element of this larger or equal space. Okay? So I need to show that this X is also inside this null space of A minus lambda I identity. Okay? So now X being inside this null space means that A minus lambda I identity square X is equal to 0. Okay? I know that this vector, this matrix times that vector is equal to 0. That means that if I take the inner product of X with A minus lambda I identity square X, this should be 0 because this vector is already 0. And if I take the inner product of a 0 vector with any vector, I need to get 0 by the overall linear properties of the inner product. Okay? So now here is what I'm going to do. I'm going to extract this A minus lambda I identity square into two parts. So this is the square of this matrix. That means this is the matrix times itself. Okay? Is equal to 0. So here is what I'm going to do now. I will take this matrix multiplication. This is another vector, and this vector times this matrix is in the second argument of the inner product. I will use the inner product property, and I will take this A minus lambda I identity to the first argument by taking its Hermitian. Okay? So A minus lambda I identity Hermitian times X, and A minus lambda I identity X is equal to 0. Okay? I have used the inner product property there. So in the topic of Hermitian matrices, we are always using L2 inner product. These are not arbitrary inner products that we consider. We are only considering L2 inner product, and we show the properties with that specific inner product. So in general, if you use another inner product, then the things that we are doing would be meaningless. So what is A minus lambda I identity Hermitian? this is A Hermitian minus Hermitian of a scalar. Hermitian of is just its complex conjugate. Okay, lambda I complex conjugate, but so I would write here lambda I complex conjugate and identity matrix Hermitian. Okay. Now this is A is a Hermitian matrix, so A Hermitian is A minus, when A is Hermitian, lambda I is real. That means that its complex conjugate is itself. And identity matrix Hermitian is going to be the identity matrix itself, because identity matrix is a matrix with real elements. So it's Hermitian, and it's also symmetric, so its Hermitian is itself. So we see that this matrix Hermitian is nothing but the same thing here. So A minus lambda I identity X, A minus lambda I identity X is equal to 0. Okay? But you see that here, this is nothing but an inner product of a vector with itself. Okay? That means that I have here A minus lambda I identity X, norm square is equal to 0. But by the properties of the norm, this vector inside should be equal to 0. This is the 0 vector, but that means that X is inside null space of A minus lambda I identity. Okay? And that completes the proof. I have taken an arbitrary vector here in this null space, and I have shown that that arbitrary X vector should be inside this null space as well. That means that this null space is a subset of this null space. And then I have proven both of these subset relationships, which means that these two null spaces should be equal. So the largest null space is reached at the first power. So the eigenspace is the largest null space. That means that here the minimal polynomial powers should be all equal to 1 for an Hermitian matrix. Okay? So now we can actually try to compare the general case and the Hermitian case. In the general case, we had the minimal polynomial in the following structure: S minus lambda 1, S minus lambda 2, S minus lambda k. But these powers m1, m2, mk can be between 1 and Ri. This is the general case. In the Hermitian case, we have the following minimal polynomial: S minus lambda 1, S minus lambda 2, S minus lambda k, and each mi is equal to 1 for all I. Now I can write also the general decomposition for the general matrices. So in the general case, Cn is decomposed into these null spaces: A minus lambda 1 identity m1, A minus lambda 2 identity m2, going until A minus lambda k identity to the power mk. And in the Hermitian case, since all mi's are 1, our decomposition would be looking like this. Cn is null space of A minus lambda 1 identity, power 1, m1 is 1, null space of A minus lambda 2 identity, power 1, m2 is 1, and I have null space of A minus lambda k identity, okay, with the power 1. Okay? This is the Hermitian case. So these are the largest null spaces in that case. If these are the largest, so these are eigenspaces as well. So I have the eigenspace for the first eigenvalue, eigenspace for the second eigenvalue, and eigenspace for the kth eigenvalue. But if these are eigenspaces, elements of these spaces should be eigenvectors. Okay? Non-zero elements of these spaces would be eigenvectors. Okay? And I have shown here that eigenvectors belonging to distinct eigenvalues would be orthogonal to each other. We have already shown that eigenvectors belonging to distinct eigenvalues for Hermitian matrices would be orthogonal. That means that eigenspace of the first eigenvalue needs to be orthogonal to the eigenspace of the second eigenvalue. That means that there needs to be an orthogonal sign here. This is not only a direct sum decomposition. In the Hermitian case, this is going to be an orthogonal direct sum decomposition, because elements of these subspaces, non-zero elements, are eigenvectors, and the eigenvectors belonging to distinct eigenvalues would always be orthogonal to each other for Hermitian matrices. Okay? That means that these eigenspaces should be orthogonal to each other. So for the Hermitian case, we not only have a direct sum decomposition, but we have an orthogonal direct sum decomposition. Okay? And in the general case, the Jordan canonical form of a matrix does not have to be diagonal. But in the Hermitian case, size of the largest Jordan block for each eigenvalue is 1, because mi is 1. Okay? Minimal polynomial power is 1. That means that the Jordan canonical form of a Hermitian matrix would be as follows. Lambda 1, lambda 1. So I would have 1 by 1 blocks for lambda 1. Okay? And for lambda 2, I would have 1 by 1 blocks, because the size of the largest Jordan block would be 1. And this is for lambda 2. And for lambda k, I have the similar structure. Okay? For lambda k, I would have 1 by 1 Jordan block. And everywhere else is 0. And because all Jordan blocks have size 1, the Jordan canonical form of a Hermitian matrix would be diagonal. Okay? And it would have the following structure. It would have structure lambda 1 times identity R1 by R1, lambda 2 times identity R2 by R2, going until lambda k times identity Rk by Rk. These eigenvalues are going to be repeated R1 times, R2 times, and Rk times. Okay? Why is that? Because here the dimensions are still R1, R2, Rk, and R1, R2, Rk here. Okay? The characteristic polynomial powers should still determine the dimensions. Therefore, the corresponding block of this matrix, which corresponding to the eigenvalue lambda 1, is going to be R1 by R1. And it's going to be a diagonal matrix with the eigenvalue lambda 1 on the main diagonal. So it's just going to be lambda 1 times identity matrix, lambda 2 times identity matrix, and lambda k times the identity matrix. So in total, the sizes of this matrix is going to be n by n, because the summation of these sizes R1, R2, Rk would be equal to n. Okay? So this is the general theory of Hermitian matrices. We have only not looked at the P matrix structure, or the properties of the P matrix for a Hermitian matrix, and we are going to see that it is also going to be very, very special. So the Jordan canonical form is diagonal, but we are going to see that even the P matrix that would bring a Hermitian matrix into its Jordan canonical form would be very, very special. Okay? And it is going to be remaining for the next lecture. Thank you very much for watching. Bye-bye.